Hello everyone, my name is Rohini Potraje, roll number BT23CME022. This is my transport phenomena assignment video on the topic equations of change for non-isothermal systems. So let's begin with section 1, the energy equation. The energy equation is basically a statement of first law of thermodynamics applied to a flowing fluid. It says that the rate of increase of kinetic and internal energy of a fluid element equals the net rate of kinetic and internal energy addition by convective transport plus the net rate of heat addition by molecular transport, which is conduction, plus the rate of work done on the system by molecular mechanisms, that is by stresses, plus the rate of work done on the systems by external forces, for example by gravity. Mathematically this is written as del by del t into of half rho v square plus rho u cap equal to minus del dot half rho v square plus rho u cap v minus del dot q minus del dot pv, which is further minus del dot tau dot v plus rho v dot g. Here we have another second equations which is rho v dot g equal minus rho v dot del del phi cap. And when results equation 2 results is inserted in equation 1, we get del by del t half rho v square plus rho u cap plus rho phi cap equal to minus del dot t dot v. When this result from equation 2 is inserted into equation 1, we get del by del t of 1 half rho v squared plus rho u hat plus p phi rho phi equals minus del dot of 1 half rho v squared plus rho u hat plus rho phi times v minus del dot q minus del dot pv minus del dot of tau dot v. Now after subtracting the mechanical energy equation from this total energy equation and doing further simplifications, we arrive at the equation of change for temperature, which is rho Cp hat times dt over dt equal minus del dot q minus t colon dv minus del ln rho over del ln t at constant pressure times dp over dt. And this is equation number 3, and this is the equation of change for temperature. Now let's look at the special versions of the equation of change for temperature. Case number 1, for an ideal gas, the quantity del ln p ln rho over del ln t at constant pressure equals minus 1. So the temperature equation becomes rho Cp hat times dt over dt equals k del square t plus dp over dt. And using Cv hat, it becomes rho Cv hat times dt over dt equals k del square t minus p times del dot v. Case number 2, for fluid flowing in constant pressure system, dp over dt equals 0. So the equation simplifies to rho Cp hat times dt over dt equals k del square t. Case number 3, for a fluid with constant density, the quantity rho del ln rho over del ln t at constant pressure equals 0. So again we get rho Cp hat times dt over dt equals k del square t. Case number 4, for a stationary solid, the velocity is 0. So the equation becomes rho Cp hat times del t over del t equals k del square t. Now moving on to the Bosnisk equation of motion for forced and free convection. The buoyant force appears automatically when an equation of state is inserted into the equation of motion. We use the Bosnisk approximation, which states rho of t equals rho bar minus rho bar times beta times t minus t bar, where beta equals plus 1 over rho times rho over del T at constant pressure evaluated at T equals T bar. Substituting this into the equation of motion gives us equation number 4. Rho times dV over dt equals minus del P plus rho bar times G plus del dot tau minus rho bar times G times beta times T minus T bar. Now to describe non-isothermal flow of Newtonian fluid, one needs the equation of continuity, the equation of motion which contains mu and k, the equation of energy which contains mu, k and also k thermal conductivity, the thermal equation of state which is P equals P of rho and T, and the caloric equation of state which is Cp hat equals Cp hat of P and T. Standard assumptions used are: first, assumption of constant physical properties, and second, assumption of zero fluxes. Now let's do the dimensional analysis of the equations of change. The three governing equations in dimensional form are: continuity del dot V equals 0, this is equation 5, motion rho bar times dV over dt equals minus del P plus mu del squared V plus rho bar times G times beta times T1 minus T naught times G over G, this is equation 6, and energy rho bar times Cp hat times dt over dt equals k del square T plus mu times phi V, this is equation 7. We now introduce dimensionless quantities using characteristic quantities as follows: x tilde equals x over L naught, y tilde equals y over 1 naught, z tilde equals z over L naught, t tilde equals v naught times t over L naught, v tilde equals v over v naught, p tilde equals p minus p naught over rho v naught squared, t tilde equals t minus t naught over t1 minus t naught, phi v tilde equals 1 L naught over v naught squared times phi v, del tilde equals L naught times del, and d over dt tilde equals L naught over v naught times d over dt. In terms of these dimensionless variables, the equations of change in equation 5, 6 and 7 takes the form: continuity del tilde dot V tilde equals 0, this is equation 8, motion dV tilde over dt tilde equals minus del tilde P tilde plus mu over L naught V naught rho del tilde square V tilde minus GL naught beta T1 minus T naught over V naught square times G over G times T tilde, this is equation 9, and energy dt tilde over dt tilde equals k over L naught V naught rho Cp hat del tilde square T tilde plus mu V naught over L naught rho Cp hat T1 minus T naught times phi V tilde, this is equation 10. Now the dimensionless groups in equation 8, 9 and 10 are for special cases. We have three regimes: forced convection, intermediate free convection and free convection. Choice for V naught: in forced convection it is V naught itself, in intermediate it is V naught, in free convection case E is root of nu over L naught, in case B it is root of alpha over L naught. The mu over 1 naught V naught rho term becomes 1 over Re for forced convection, 1 over Re for intermediate and 1 for free convection case A, and PR for free convection case B. The gravity buoyancy term becomes neglect for forced convection, GR over Re squared for intermediate, GR over Re squared for free convection case A, and GR times PR squared for case B. Now let me continue with the table of dimensionless groups and then give their physical interpretation. K over L naught V naught rho Cp hat equals 1 over Re times PR for forced convection, 1 over Re times PR for intermediate, 1 over PR for free convection A, and 1 for free convection B. Mu V naught over 1 naught L naught rho Cp hat T1 minus T naught equals Br over Re times PR for forced convection, Br over Re times Pr for intermediate, and neglect for free convection cases. Now the physical interpretation of these dimensionless groups. Reynolds number Re equals rho V naught squared over L naught divided by mu V naught over L naught squared, which equals inertial force over viscous force. Froude number Fr equals rho V naught squared over L naught divided by rho G, which equals inertial force over gravity force. Gr over Re squared equals rho G beta T1 minus T naught divided by rho V naught squared over 1 naught L naught, which equals buoyant force over inertial force. Peclet number Pe equals Re times Pr equals rho Cp hat V naught T1 minus T naught over L naught divided by K T1 minus T naught over L naught squared, which equals heat transport by convection over heat transport by conduction. Brickman number Br equals mu V naught over L naught squared divided by K T1 minus T naught over L naught squared, which equals heat production by viscous dissipation over heat transport by conduction. Now question 1, viscosity variation and velocity gradients in a non-isothermal film. Water is falling down a vertical valve in film 0.1 millimeter thick. The water temperature is 100 degrees Celsius at the force free liquid surface and 80 degrees Celsius at the wall surface. Part A, show that the maximum fractional deviation between viscosities predicted by equations 11.4, 17 and 18 occurs when T equals root of T naught times Ts. And solution is, the fractional deviation becomes two viscosity equations is epsilon of T equals mu 17 of T minus mu 18 of T, all divided by mu 18 of T. And setting D epsilon over dt equals 0 and solving n over T minus B over T squared equals 0, which gives T equals B over n, where B equals ln of mu naught over mu s divided by L over T naught minus 1 over Ts, and n equals minus ln of mu naught over mu s divided by ln of T naught over Ts. Text equals T naught times Ts times ln T naught over Ts divided by T naught minus Ts, which approximately equals root T naught times Ts. Part B, calculate the maximum fractional deviation for the conditions given. Solution: T naught equals 373.15 Kelvin, Ts equals 353.15 Kelvin, Text equals root of 373.15 times 353.15 equals root of 131749.5, which is approximately 363 Kelvin. Viscosities of water at the boundary temperature mu at 373.15 Kelvin approximately 2.8 times 10 to the minus 4 Pascal seconds. Mu at 353.15 is approximately 3.54 times 10 to the minus 4 Pascal seconds. Fit constants: B equals ln 0.7966 divided by 2.679 times 10 to the minus 3 minus 2.831 times 10 to the minus 3 equals 1494.1 Kelvin. N equals 0.2271 divided by 0.05509 equals 4.122. Viscosities at Text mu 17 at 363 Kelvin equals 3.164 times 10 to the minus 4 Pascal seconds. Mu 18 at 363 Kelvin equals 2.980 times 10 to the minus 4 Pascal seconds. Now the maximum fractional deviation. Epsilon max equals 3. Epsilon max equals 3.164 times 10 to the minus 4 minus 2.980 times 10 to the minus 4, all divided by 2.980 times 10 to the minus 4, which equals 0.062. Further again we have question second, third and fourth of similar topic based on equations of change of non-isothermal systems, which we can refer from my document or PPT. Thank you.